Close your eyes for just a second and imagine stepping outside on a beautiful, clear summer morning. Almost instantly, you feel the warmth of the sun on your face, right? It's a feeling we all know and absolutely love. But, if you stop and think about the physics behind that exact feeling, it actually presents an incredibly fascinating puzzle. Welcome to This Explainer. Today, we're going to unlock exactly how that warmth travels all the way across the solar system just to reach you. And we'll break down the incredible science behind the radiation of heat.
Okay, let's dive into this. Here is the core paradox we really need to solve. How does heat from the sun actually reach Earth through the vast, completely empty void of space? You see, conduction and convection strictly require some kind of material medium, like fluids, gases, or solid objects, to move through. But the vacuum of space? It has none of that. It's empty. So how in the world does the heat make that massive journey?
Section 1. The Vacuum Mystery. Introducing the invisible hero.
And that invisible hero is radiation. Radiation is the transfer of heat in the form of electromagnetic waves, mainly infrared radiation. But here's the crucial part. Its absolute superpower is really the second half of that definition. It doesn't require any material medium whatsoever. Unlike conduction or convection, these electromagnetic waves can travel perfectly well through a complete and total vacuum. That lack of reliance on physical matter, that is exactly why the heat from the sun can successfully traverse millions of miles of empty space to finally warm our planet.
Let's move on to Section 2, the rules of heat transfer. How thermal radiation behaves.
Now, what's really interesting about this slide is that you might think only obviously hot things, like a roaring campfire or the sun itself, emit thermal radiation. But the reality of physics is actually way broader than that. Absolutely every single object with a temperature above absolute zero emits thermal radiation. Literally everything. That means everything around you right now, your desk, your coffee mug, even an ice cube sitting in your freezer is constantly acting as a source for these invisible thermal waves.
Of course, not all objects radiate the exact same amount of heat. There's a simple universal rule of thumb at play here. Hotter objects emit more radiation than cooler objects. It's just a direct correlation. The higher the temperature of the object, the greater the volume of these invisible infrared waves it pumps out into its surrounding environment. So, while you and a glowing campfire are both emitting radiation right now, the immensely hotter campfire is pumping out a vastly larger amount of it. So these waves travel outward through space or air until they finally hit a destination. And when thermal radiation reaches another object, three specific things can occur. First, some of that radiation is absorbed. Second, some is reflected, just bouncing right off the surface. And third, and this depends entirely on the material itself, some might just pass right through it. Every single time a thermal wave hits a target, it's undergoing a mix of absorption, reflection, or transmission.
But here is a fascinating distinction, and it's a really important one. Out of those three options, absorbing, reflecting, or passing through, it is strictly the absorbed radiation that actually heats up the receiving object. If a wave bounces off you or passes right through you, it doesn't make you any warmer. Only the absorbed fraction increases an object's temperature.
Which leads us to Section 3, absorbers versus reflectors. Not all surfaces are created equal.
And this brilliantly illustrates how visual properties actually dictate thermal properties in a massive way. On one hand, you have black, dull surfaces. These are fantastic absorbers of heat, and as a result, they're also very good emitters. On the flip side, white, shiny, or polished surfaces do the exact opposite. They are very poor absorbers and emitters, but they are exceptionally good reflectors of heat. So the visual nature of the surface, whether it's dark and matte or bright and polished, fundamentally changes how it handles that incoming thermal radiation.
Section 4. Radiation in everyday life, harnessing the physics of heat.
Now, we naturally use these rules of physics to our advantage all the time, honestly, often without even realizing it. I mean, why do people generally choose to wear light-colored clothes in the dead of summer? Well, it's because white and light surfaces are excellent reflectors, bouncing the sun's radiation away to keep you cool. Or consider a thermos, keeping your coffee hot on a winter morning. It intentionally uses a highly polished inner surface. Being shiny, it acts as a poor emitter and a great reflector, basically bouncing those thermal waves right back into your drink instead of letting them escape into the cold air.
But this goes far beyond just choosing a summer wardrobe or keeping a beverage hot. Mastering the physics of thermal radiation actually empowers us to engineer a better society. By deeply understanding how these waves work, we can design vastly more energy-efficient buildings, innovate highly efficient solar heaters that harness the sun's boundless energy, and even develop advanced thermal insulation that protects us from extreme environments.
The rules of thermal waves are literally built into the infrastructure all around us.
We've explored how radiation transfers heat through the vacuum of space, how everything emits these waves, and how color totally dictates absorption and reflection. So I want to leave you with this thought. Take a quick look around the room you're sitting in right now. Based on the colors and textures sitting right next to you, what invisible thermal waves do you think are being absorbed? And what waves are bouncing off your surroundings this very second? The physics of heat is happening everywhere, all the time, completely unseen. Thanks so much for joining me for this explainer, and keep looking closely at the world around you.